So now we have lists, ordered sequences of arbitrary elements, but they can be mutable. We've already seen some operations on them, but there's a lot of other operations that we'd like to have, and we do have on lists. So for example, we can iterate over them. What does that mean? It says inside of a for loop or a while loop, but certainly inside of a for loop, I can have a call with a loop variable that's iterating over that structure. And let's look at an example of it. So I've already bound that variable univs. And so this says I'm going to let E in turn be each element in univs. And I can do things like print out some information about them. And since each of those elements is itself a list, I can have another loop where I loop over E, letting U be each element inside of there, and I print something out. And if we just go over to my idle screen here, okay, I'm just printing out, so what's the value of univs? What's the value of univs 1? And then at the bottom you can see that loop, where in fact I print some information and I loop through each of the pieces inside of that structure. As with tuples, what that iteration is doing is it's setting up an internal index, starting at 0, and walking down each element of the list until it gets to the end of the list, with the index pointing to each element in turn, letting me extract it, do something with it. And that something might be, in fact, printing or looping over that interior structure. So I've got iteration. Just sounds pretty nice. What else do I have? Well, we've already seen that I can add things to lists, and I did that with append. And if again I go over to my idle shell, I can do tech appends. In fact, before I do that, let's just remind you, tex is a list of MIT, Caltech, and RPI. And suppose I say I'm going to do tex, and I'm going to append to it the IVs. If I now look at the value of tex, aha, as I would have expected. Remember what we said about append. It's a method, just why we got that funky little period there. And it's a method that in fact has a side effect. It mutates. Okay? It causes a side effect in which in particular I'm going to take text as a list and I'm going to change the end of it to add a new element in. And this new element in this case was itself a list. So the structure is now a list 4 long, the first 3 elements of which are just strings, the 4th element of which is a list. And that's what got printed out there. Now suppose I said that's nice, but I don't want to have a whole list hanging off as an appendage. I'd like to have a list with everything at the same element. I'd like to flatten them. In that case, what I really like to do is to take 2 lists and concatenate them together. It's called flattening, and we can do that using the plus operator. So I'm going to reevaluate these pieces again. Let me just bring them back into my environment. Again, I'm running through that loop. Because now what I'd like to do is just go back to where I had with text before. There's text. And I'm now going to ask flat to be a name for what I get by concatenating text and IVs together. The plus sign saying just do a concatenation. And if I look at flat, nice. It is a sequence, a list of elements all at the same level. So append sticks something in at the end of a list. Addition or concatenation puts copies of 2 lists together. And notice it creates a new list. And to see that, let's see what happened with text. Yes, it has not changed, and neither has IVs. That's actually important. And so to look at that, what that's really saying is that in the case of append, I am mutating. I'm changing one of the lists. In the case of concatenation, I'm creating a new version of those lists. I'm literally creating a copy of it, and then adding a copy, if you like, of the second list to it as well, which allows me to separate out different ways of thinking about how I might want to manipulate lists. So I can mutate when I need to, but I might want to just make copies when I need to, and I can do that. Let's look at one last example. And this is going to look at an example of both where things can go wrong when I'm iterating over lists and how I get around that. And for that, I'm going to bring up a new piece of code. And the piece of code here is going to be something that's going to look at removing duplicates in a list. So the idea is, I want to have 2 lists, and I'd like to get back a list with just those elements that only appear once inside of the list. So I could write a little loop to do it. Here it is. I'm going to remove duplicates. I've got 2 lists, L1 and L2. I'm going to loop over L1. And I'm going to say for each element in L1, if it's in L2, let's just remove it from L1. And again, remove is a method. There's the dot. Don't worry about the details of it, but it basically takes the list L1, takes the first instance of that element E1, and takes it out of the list by mutating. So let's look at what happens if we do this. And in fact, we can load this up into our idle shell. And if I do that, let's look at what happened here. So L1, in fact, let's look at it in a little bit more detail. L1, I'm going to start off as the list 1, 2, 3, 4. L2 is the list 1, 2, 5, 6. And I'm going to remove the duplicates between L1 and L2. Ideally, I would like that to be just having the element, the list L1 be those elements that are not duplicated in L2. But if I, in fact, look at what L1 is, printing it out, I get the list 2, 3, 4. So why does that happen? Well, let's look at that in a little bit more detail as well. The problem is that inside of the loop, Python is keeping track of where it is in the list using this internal counter. We already said as it iterates over L1, it's keeping a little index that says where it is. When I decide to remove something from L1, I'm going in and changing the list, but I don't adapt the counter. So I can literally change the list by 1, which means the counter is now pointing to a different place in the list. Because if I shorten the list by 1 by removing something from the front, counter, if it was pointing, for example, at the second point in the list, is now pointing at the third point in the list. So when we mutate a list, we change its length, but Python cannot adapt to that. And obviously that's a problem because it doesn't do what we like. So when we are doing mutation on lists while iterating over them, that's probably not a good idea, at least not on the list we started with. So how could we do this better? Well, let's clone. And what does clone say? It says, let's make a copy of the list. And I can do that with this very simple form here. If I take the list L1 and I say in square brackets, just the symbol colon, it says, gives me all the elements from the first to the last, but make me a copy. And now I can loop over L1 start, but mutate L1. So this is changing L1, but this is looping over a copy of L1. And if I do that, which was the second piece of code I had there, that's why, in fact, it will print out just 3, 4. It removes the 1 and 2 from L1, because those are duplicates, but it does it without getting confused about where it is inside of pieces. And so what this says is that we want to use L1, a copy of L1 as L1 start. And notice, by the way, I actually have to make a copy. If I were simply up here to have said instead, let's use L1 start just to be L1 rather than L1 with that funky thing at the end, it would not have worked. Why? Because if I say this form, L1 start points to the value pointed to by L1, which is the list itself, and I'm back to the first state. By using L1 with the colons, I literally make a copy, and now I can walk down a copy, checking for duplicates, while changing the original list itself. So now we've seen properties on lists. We can iterate over them, and we can do it while mutating them, and when we need to, we'll want to use clones to make copies of lists so that we make sure that we keep track of where we are inside of that structure.